So where we left off was at section 9.10, which I said is arguably the most important section of all of chapter 9. Every reaction has its place. They're all important. However, what makes chapter or section 9.10 unique is that we learn a new way to make carbon-carbon bonds. And making carbon-carbon bonds, I mean, carbon-carbon bonds are ubiquitous in organic chemistry. They're in almost every molecule that we see. But are they easy to make? The answer is no. And so if you remember, we could take a terminal alkyne and we could deprotonate it completely with sodium amide. Now we said, okay, we could take it then and we could treat it with water, and then we'd go right back from whence we came, okay? But there's no point in doing that. Um, there's no point in taking the compound, deprotonating it, and protonating it again. And so what we're going to see now is if we take it and we treat it with an electrophile, like something like iodomethane, is that we can do an SN2 on that. And then what we do is we add a carbon to the chain. So we end up with a carbon on the end. And you see that summarized down here, that we can do an SN2 reaction with an alkyl halide and our alkanide. So now we have a way to make where's my highlighter? A way to make a carbon-carbon bond. And, it's a very big deal. It's not a joke. Making carbon-carbon bonds is actually a very big deal for scientists. It's not an easy thing to do. So it says alkylation with an alkanide is SN2. And so it's going to work best if you have a methyl or a primary alkyl halide. You're mostly going to get E2 with the secondary halide, and you're only going to get E2 with a tertiary. But again, it is a way to make a new carbon-carbon bond, and therefore it is a big deal in organic chemistry. Now, if you have a terminal alkyne, well, there's only one hydrogen on the as part of the triple bond. But what if you have acetylene, right? Acetylene, which you know is this compound, acetylene has two hydrogens on it. So if you're wondering, could I do a dialkylation or successive alkylations? The answer is yes. You could do two successive alkylations. So you deprotonate once, and then add do your SN2 reaction, and then you deprotonate again. So we could say deprotonate again. Okay, so second time, and then you do your second SN2 like that. I'm going to write down here, order is not important. Okay, so let's say you wanted to add two alkyl groups. Let's say one's a methyl, one's an isopropyl. At this level, I don't care which one you add first. As long as you add them, that's good enough for me. Okay, order not important. So let's say you wanted to make this compound. So this is what? This is 2-pentyne, and you're starting it with acetylene. Well, you have to add an ethyl group on it, and then you have to add a methyl group. So you can see they deprotonated. They used ethyl iodide to put in the ethyl. Then they deprotonated, used methyl iodide to put in the methyl, and there you go. So complex target molecules can be made by building a carbon skeleton and converting functional groups. And this is how we get to things like new drugs, new medicines that we can use to extend and enhance human lives, are by finding ways to make carbon-carbon bonds. Because if you look at the structure of most marketed drugs, they're actually pretty complicated. And so it takes a lot of skill to make those compounds. And therefore, the more the greater ability that we have and the more options we have for making carbon-carbon bonds, the better off we are as humanity, really. Anyhow, so it says starting with acetylene, which you guys know is just ethyne, right? It's got two terminal hydrogens. It asks us first to make 1-butyne. So what's 1-butyne? 1-butyne would be this compound here. Excuse me. So you can see that all you need to add to your acetylene is an ethyl group, right? So we're going to start out with acetylene. And what we're going to do in the first step is we're going to treat that with sodium amide. That's going to form the sodium acetylide. And then in the second step, we're going to treat that with ethyl iodide. And that is going to give us our 1-butyne, like that. The second one, we have to add this is called a benzyl group on one side. And then we have to add an ethyl group on the other side. Now, again, I told you order is not important. So just to give you a little more background on, the mechanism, normally we put all the steps together, but let's just say I draw this out explicitly. The sodium amide, like this. We'll put in the proton. It's not asking us to draw a mechanism, but let's just do it. So then we end up with sodium acetylide, which is going to be this, okay? And then let's say we wanted to add the ethyl group. So then we're going to treat it with ethyl iodide. So ethyl iodide like this. So this is going to do an SN2 like this, nucleophilic attack, loss of leaving group. And we end up with 1-butyne in this case. And then to get to the final product, I'll just go a little faster. We're going to treat it with sodium amide. And then in step 2, we're going to treat it with benzyl chloride, or you could choose benzyl bromide or benzyl iodide. I'll choose benzyl chloride, and that is going to give us the final product. And again, order of the ethyl iodide and the benzyl chloride, not important. Okay, you can put whichever one you want on first. Okay, give me a thumbs up if you think you could make those kind of compounds. 1-butyne or this other. Cool, awesome. That's great. So now, in terms of synthesis strategies, we've finished. So now, as far as the new chemistry, we are done. Okay, so we finished all the new chemistry. But in terms of synthesis strategies, what are some of the major take-home messages we've gathered in this chapter? One, I would say, is converting a triple bond to a double bond using Lindlar's catalyst. That gives you a cis double bond. If you use dissolving metal reduction, you make the radical anion as an intermediate, and so you end up with a transalkene in that case. So we've gone over all of those. We've even learned how to go from here to here, really. We've learned how to do, if I wanted to go from here to here, I would just do halogenation. So I'd use, bromine, and then I'd use excess sodium amide, right? Followed by, come on, Mr. Dion, followed by water, right? And I could do the double elimination that way. So now we've worked out all kinds of different manipulations here. The only thing we haven't learned how to do in this section is how to take an alkane and convert it into an alkene, but that's something we're going to see in chapter 10. If you're wondering what CCl4 is, that's carbon tetrachloride. That's a solvent. That is the solvent. I don't demand that my students put that in. If you want to, you can, but you don't have to. But anyhow, so we've learned all those transformations. And then these are all the different reactions that we've covered. So I've gone over these already, but let's just review them one more time. Okay, and then we're going to take a look at some practice here. So we'll just go from 1 to the end. So reaction number 1, so that's our double elimination followed by protonation to make an alkyne. Reaction number 2 is hydrohalogenation, Markovnikov addition. Reaction number 3, that's the addition of one equivalent of HX. So we end up with a vinyl halide in this case. Then we learned Markovnikov addition of H2O, and we talked about the enol and the tautomerization. Then we learned anti-Markovnikov addition of H2O. We covered that. Then we covered a halogenation with one equivalent of a halogen to get a dihalide, and you'd get a mixture here, but of cis and trans. But yeah, anyhow. The trans is going to predominate. Then what else? We talked about making a tetrahalide using excess halogen. We talked about ozonolysis and how you end up with a carboxylic acid. If you have a terminal alkyne like is shown here, you end up with CO2 gas as well. We talked about reduction using sodium metal to make a transalkene with Lindlar's catalyst to make a cisalkene. We talked about in the last section, so this is 9.10. We talked about alkylation, so deprotonation followed by an SN2 to add a carbon onto your molecule. And then we talked about complete reduction of our triple bond using standard hydrogenation conditions that we learned in chapter 8. So there you go. So somebody asked me, do you have a summary of all this? Well, I'd say if you look at question 9.37 in the textbook, it's not a blank one of these, but it's pretty close to it. Okay, so you could get some practice on all of these reactions. But let's see if we can, do a couple of transformations here. I might switch to a blank document for these to make sure I don't run out of space. But the first one is asking us to take 1-butene, so this compound here, and then we want to make cis 3-hexene would be this compound here. So I'm going to switch over to a blank document, and then we'll give this one the old college try. So this is question 9.29, so just bear with me, and I'll scribble it right here. So question 9.29, and this is A, and we're starting it with 1-butene, and then we want to make, what was the, am I looking at the wrong one? Just let me double check. I have a good memory. It's just very short, huh? Anyhow, yes, it was 1-butene, and then I had the wrong compound written down in my scratch paper. Anyhow, then we want to make cis 3-hexene. Okay, well, you can see that we're adding 2 carbons to the molecule. And so at some point along the way, we're going to have 1-butyne and then do an SN2 with ethyl iodide. And then we can reduce that to the cis alkene using hydrogenation and Lindlar's catalyst. So now the question becomes, well, how do we get from the alkene to the alkyne? Well, that involves halogenation. So if we treat this with bromine, and you can include a solvent like CCl4, you don't have to. I'm going to leave it out. That's going to give you the dibromo compound. Stereochemistry, not really important because we're going to do a di-elimination on this. So then if we treat it with excess sodium amide, followed by treatment with water, we're going to end up with our 1-butyne molecule like that. And now we can add the 2 carbons. So we're going to treat that with sodium amide, followed by ethyl iodide or ethyl bromide, doesn't matter. And that's going to give us 3-hexene. And now we can reduce that to the cis alkene using hydrogenation conditions and Lindlar's catalyst. Like that. So that's a total of 1, 2, 3, 4, 5, 6 steps. This is a 6-step synthesis. I don't see any other way of doing this one. So 6 total steps for that one. The next one, we're starting it with 1-butene again. So this is 9.29B. 9.29B, we're starting it with 1-butene again. And now we want to make this aldehyde. So this is called butyraldehyde. So there's no change to the carbon skeleton here. How do I know that? Because we're starting out with 4 carbons and we're ending up with 4 carbons. So that means this has to come from 1-butene. And of course, for that, we're going to do anti-Markovnikov. So anti-Markovnikov addition of water across that triple bond using 9-BBN. And so to make the alkyne, it's going to be the exact same conditions that we used before. So first, we're going to brominate that. That's going to give us the 1,2-dibromo butane. Then we're going to treat that with excess sodium amide, followed by water. That's going to give us our 1-butyne molecule. And then to go here, we're going to do anti-Markovnikov addition of water. And so that's going to involve 9-BBN. The first step and the second step is going to be hydrogen peroxide and sodium hydroxide. And keep in mind that the enol that we're talking about here is going to be this. So it's going to look, man, I can't get that bond to look good. There we go, that's decent. So we're going to end up with this enol, and that enol is going to undergo tautomerization to give you the aldehyde. Yeah, looks good. All right, so now let's take a look at 9.29C. So this is 9.29C, so 9.29C. And in this one, we're starting it with 1-butyne, kind of fresh in our brains. We use it both times. And now we want to make this alcohol. This is called 2-butanol. You can probably guess where that name comes from, 2-butanol, right? So if we have 1, 2, so butan, and you just change the suffix from "ane" to "all." So for this one, what are we going to do? We need to make a double bond, and then we need to do a Markovnikov addition of water across that double bond. So this one's actually a little bit quicker than the others, okay? Do I have the compound written down correctly? Yeah, I do. Okay, so all we need to do is we need to reduce it. And to reduce down, if you have a terminal alkyne and you want to reduce it to a terminal alkene like this, the only way to do it is to use H2 in Lindlar's catalyst. I didn't mention this during the lecture, but if you try dissolving metal reduction to take a terminal alkyne and convert it to a terminal alkene, it doesn't work. Okay, so the only option is H2 in Lindlar's catalyst. And then after that, we would just do a Markovnikov addition of water across the double bond like that. Okay, so remember, if it's a terminal alkyne and you want to make a terminal alkene, you cannot use a sodium metal reduction. You've got to use hydrogenation for that. Just give me 1 second here. So we covered all of those. Let's see here. Let's try another one, okay? Let's try one more, okay? And we'll come back and do the rest on Monday, but I do want to do one more with you, okay? This is 9.29E. 9.29E is a pretty interesting reaction because you've got to take one butane and then you want to make this compound, where one bromine is coming up like this and the other bromine is coming down like this. So there's a few moving parts to this thing because not only do you have to change the carbon skeleton, right? Because you're starting out with 4 carbons and then you have to end up with 6 carbons. So that's fine. I mean, we know how to add the two carbons on there using sodium amide and ethyl iodide. But remember that bromination is an anti-addition. And so that means we have to have the trans alkene start with. You can't use the cis alkene. So you can't do this reaction with this, okay? This will not work. You have to start with the trans alkene. So then what that means is after you have appended on the ethyl group, so first step, sodium amide, second step, iodoethane, you're going to end up with your 3-hexyne. But in order to convert that into the trans alkene, the only possibility you have there is sodium metal reduction. And then, right, you're going to end up adding one bromine on the one face of the molecule and the other bromine on the opposite face of the molecule. So you're going to get this compound, plus it's an enantiomer. And the reason I bring this up is because the alkenes are going to come back and we're going to be looking at things like dihydroxylation, whether it's cis or trans, or syn or anti-addition, and then bromination, which is always anti-addition. All right.